So I'd like to talk about data entry. Probably the most boring, but also one of the most important parts of geographic information systems and our geographic analysis, because your analysis are only as good as your data. And so we have to get the coordinates and the attributes accurately into our GIS data layers. There are the main points here that digitizing our coordinates takes time. I don't know how many projects I've advised on where people were surprised at the effort it took and money it took to get data into the GIS at the level of accuracy that they wanted. Modern digitizing is using GPS, GNSS, they're called generally, and image interpretation. So we use satellites or aerial platforms to capture information in digital images, and then we interpret those digital images. We'll talk about both of those methods of entry in detail in the next couple of weeks, the next couple of chapters, but they're the base for which we use to digitize. The magnification of the image greatly affects our digitizing accuracy. So there's the inherent accuracy of the materials, and then in the images, there's the magnification. So both those things have to be right. But while digitizing, the thing we can control when someone's given us some imagery is how far we zoom in or out. But there's a trade-off. The more you zoom in, the smaller the area, the more you spend time panning between different areas, and the harder it is to digitize rapidly. The more you zoom out, the more a small mispointing error makes a difference in the distance on the ground, the scale distance on the ground, the larger your error. So you have to balance those two. We spend a lot of time working with what's called the topology, the connectivity adjacency, the correct net, getting a mesh that is complete but doesn't overlap in polygon data layers or in network or line data layers. So we have to work with that. We sometimes thin or interpolate, expand our data as we've digitized to get the boundaries at a higher or lower point density throughout our data layer. So how do we used to collect it? Laboriously, using optical instruments and pulled physical chains, or committing it to paper both in the collection and in the dissemination. But now we've gone full digital, so use digital cameras on planes that are located with GPS, or in the field collecting data with GPS, and then interpreting what the features are on the image and drawing or connecting the dots. This direct measurement is probably the best, but there are certain things, mostly area features, where it doesn't make sense to measure them directly. That's why we use an image. For point features, many of them, and for line features, many of them, roads, for example, we can put an apparatus on a moving vehicle or have a person carry it to a key location and measure the coordinates of those and any attributes. So we're doing image interpretation. We used to do image interpretation on physical hard copy maps. There was a period of time where we took all that data that we digitized in the field, or that we collected in the field, I should say, and put it to maps, and we digitized that information off the hard copy maps. So almost no backlog left. So on images, we're laboriously displaying and then collecting boundaries, like the boundary of the lake. We hold a puck over a location and press a button to say, here's the edge. Now, there's a lot of automated image processing, and image processing gets better and better, so we can pull a lot of these edges out, like water land boundaries, pretty effectively using automated digitizing. But there's a lot that the human interpreter can see, especially with vegetation types, or small nuances using things like texture and different shades and height information inferred from shadowing that image processing can't get still. It's getting better each year, but we still have to do a lot of digitizing, particularly for things like vegetation or things that change subtly. So we digitize boundaries, connecting the dots one after another. So point after point to make line segment after line segment to make polygons. Now, as I said earlier, we have to be cognizant of map scale, or really image scale, it's the ratio of a distance on the image to the distance on the screen. That's commonly reported as a unitless ratio, like 1 to 100,000. 1 inch on the screen equals 100,000 inches on the ground. Or as something like a unit ratio, 4 inches to a mile. The unit ratio doesn't make sense anymore, and on maps we'll put scale bars, but we're usually doing it as a unitless ratio because the computer can look at the digital image and say what a distance is, and then look at how it's displayed at the zoom we've asked for and give us this unitless ratio. This 4 inches to the mile makes no sense in a digital environment because 4 inches depends on the display. So a distance of 4 inches may be the whole image or just a tiny portion of it if we zoom in or out. So the printed scale bar makes sense on a digital output, and then you can just calculate in a display what the unitless ratio is. But you got to pay attention to it because as you zoom in to larger or smaller scales, you're going to have different distances, and so any error in pointing and collection or ability to view things gives you a different error in the data that you capture. So the more blown up things are, the larger the scale, the more accurate the positioning. But you don't want to go in too far beyond the accuracy, for example, of the image itself, because I said earlier, it affects the efficiency. You have to zoom and pan back and forth. And when you're digitizing, the project often puts a limit. You want to digitize at a scale of between 1 to 5,000 and 1 to 20,000. Don't zoom in more or less, because those are kind of the bounds of efficiency and accuracy, and then you have to pay attention while you digitize. It's better to think of the grain size or resolution of spatial data, and that's both the pixel size and the accuracy. You want the pixel size of an image to be about what the accuracy is. You don't want a really fine pixel size like 1 inch and then only have 3 foot accuracy or 1 meter accuracy, because you're wasting all those pixels. They can help you see things, but if you digitize off them, you don't get any additional information in terms of the accuracy. So you want to try and balance those, try and match those as close as possible. The extent is the area covered, the magnification level is the zoom. So when we're digitizing, we're basically doing something like this. We're tracing the location of important coordinates. And so we have to effectively drag the cursor across the landscape, but we're doing it on an image to collect the positions of those features, right? Things to know about digitizing. All maps or all imagery has spatial and categorical generalizations. If you interpret a data layer from an image, you have to basically define if you're going to put these into polygons, homogeneous regions, or homogeneous line segments. Any variation in the blob that you draw gets subsumed into that blob. It doesn't matter if a human or a machine does it. These categorical data layers have generalizations. So, you can see here that I have this polygon which may be developed. But in that developed polygon, there's buildings and parking areas, as you would think, but also patches of trees and grass and vegetation that's intermixed. This is fairly homogeneous. This is maybe a fairway polygon. So there's a variation in how uniform the polygons are. Now, if a machine does it, it does the same thing. This is a machine segmentation, and at 2 levels of categorization of specificity. And so this polygon, which is grass, gets split up into a bunch of different polygons of different grass types. So there's generalization that goes on, both by the machine and by the human. We also do spatial generalization, so we'll move things and shift things around. And this shows different kinds of generalization, both categorical or agglomerative. So this is the truth. We have a representation where these are all the, let's say, lakes. Here they're grouped because the person doesn't want to resolve between them. Or you can offset. So when you digitize a road, you want to show it as different from where the group is. Or you can omit things. So I want to digitize with a certain level of detail, but the small ones I don't. In producing or outputting your data, there's also some exaggeration generalization. You want to make a symbol wide enough so people can see it for a road, but it might be smaller or wider than the actual width of the road. Finally, there's always categorical generalization. We have inclusions that are too small to resolve inside our polygons, but they just get called that inside. So this marsh and fen are different in one data layer and another layer. They're the same thing. This might be one whole polygon. You have to be careful. Now, there's a pointing accuracy available with any person equipment combination. If I have a digitizing puck that I'm digitizing on screen, it can only point so closely, and there's a variability in the person's attention to detail, and so there's a distribution around the intended point that adds error. So there's this sort of fuzzy variability. If you have the same person digitize the same line 100 times, they're not going to fall all along the same path. And if you have 100 people digitize the same line each once, again, you're going to have variability around where that boundary is. So it's kind of a fuzzy set of locations. When we talk about accuracy, what we're trying to do is keep that fuzz, that uncertainty within a range. So we'll zoom in as much as we can with the time we have to digitize to try and reduce this. But when we're digitizing, we also have errors, always. So we have undershoots of them. This is a polygon I'm trying to complete, but I don't connect all the way. Or I might not put a node in when I should, and so I get these weird overlapping polygons. Or I might have dangling nodes. It was supposed to end here, but it hangs over, so my network might be goofy. Or I might not add label points to the inside of a polygon, so we don't know what the identity of that polygon is. So typically we digitize and then we clean. Now, how we digitize can substantially reduce the kind of cleaning we have to do. But this cleaning can be manual. We can go in and identify features. So we'll go in and say, oh, here's a polygon that shouldn't be there, and select it and delete it, right? We can manually remove it, so we can select it and make it go away. So there isn't a fairway where one shouldn't exist inside this other polygon. We can also do things. We have a host of tools. For example, there might be polygons. Oh, I digitized these 3 counties wrong. Actually, I didn't, but for the sake of example, I can select them and then merge them, use a merge tool to combine them. And then I want to split them along the real county boundary, right? So I can select it and use a split tool to split. So use this splitting and merging and adding and subtracting and a number of other tools, which we'll use and practice in the lab to craft the polygons that represent the features we want. We spend a lot of time on topology, getting topologically correct data, and we introduced topology earlier in week 1 in chapter 2, where we talked about being the proper network, a proper fabric that doesn't have polygons that overlap or lines that don't connect. We make a planar topology that has no gaps nor overlaps, and we can set up rules to enforce that topology, and while we're digitizing, have our software check that topology. So we can look for gaps and overlaps. So here's a layer. This is a sort of land cover layer, and I have a polygon here that overlaps part of another polygon and has a gap in an additional polygon. If I calculate areas for either individual parcels or for the sum of parcels, I'm going to get a wrong answer, and I don't want that. So I can do something. Our primary weapon when we're digitizing is a thing called snapping, where if we have points within a distance of a line or another point, they get forced to be together. And if I judiciously set this snapping tolerance, these sticky ends connect to things. I don't want to set it too big because I can't resolve anything smaller than the snapping tolerance. I don't want to set it too small because then it doesn't do any work for me. So typically what I'll do is set it at some level that's related to how I'm going to zoom and what I can see, and make sure things snap as I'm digitizing. Then check for topological errors and fix those few that fall through the cracks. Now when I digitize, sometimes, or when somebody gives me data, sometimes I have too few vertices, and so I can try to basically smooth curves by fitting and adding vertices. So there's various vertex density management tools. So I can sort of smooth the line. This often happens in built environments when we have coarse data and we want to smooth to like bent. cul-de-sacs. How we do that is using various tools. A common one is a thin plate splines. So it basically fits a polynomial equation into segments, then it'll fit another polynomial equation to another segment, and then make sure at the join point that they have the same slope. Now this is showing it in 2 dimensions, but I do it in 3 dimensions with plate spline, so I can get a surface if that's what I want, or in this case is a line segment at the edge of 2 polygons. This is 2-dimensional. Another thing can happen, especially with image data that's automatically classified, is I can get way too many vertices. I'm storing a bunch of vertices that don't give me any information on the change in shape. So there's various line thinning methods that really have to do with looking at a segment and then looking at lines that are intermediate, points that are intermediate in the line, actually, that are outside of a significant distance from the line trajectory. And if none of them are outside, they're basically giving me the same information. And so I can get these line thinning algorithms that look down the line and say, look, I'll look at 4 points ahead and then 3 points and 2 points ahead, and any of them that fall outside, I'll get rid of. So here I have basically 4, and these fall outside. I'm sorry, any that fall inside I'll get rid of, I shouldn't say, because if they're outside my important distance, then they do actually show a change in direction, and I want to keep them. And so these 2 fall outside when I'm 4 away, and so they show a significant deviation, but then this one doesn't fall outside. So from this segment to this segment, it really isn't adding what I consider important shape information, and so I can throw it away. And then I'll go to the next 4 and back up, and these all fall outside, and go to the next 4 and back up, and these fall outside. Oops, this one didn't. And so I identify those. Now clearly, if you expand the width, you're going to throw out fewer, and if you narrow it, you're going to throw out a lot. So if this band gets thinner, if you narrow the width, you're going to throw out more. And so how wide you make this segment has an impact, and the thinning algorithm depends on its parameters. And if you look further down the line, you also will likely throw out fewer, because you're basically looking across a longer length, and there's likely to be more deviation. So it depends on the parameters, and different thinning parameters will throw out different vertices for the same line. Same with different algorithms. So you typically have to work with a data set to find out what kind of parameters give you a thinning that doesn't change your line segments too much. Final thing I want to talk about is this notion of getting different representation of the same feature. You have it when you have redefinitions, redigitizations of a point in time, or you have it when you have 2 different layers produced from different media or by different people, and you're trying to bring them together. So you might have a border from a county map and a border from a state map, and they're not the same, and these cause conflicts. Now, this is really a bad sort of thing to happen, because you typically get these lines that overlap back and forth. So you have gaps where you have no information, it's in neither county, and gaps where it's in both counties or both states, whichever it is. And then you have a bunch of tiny polygons where they go back and forth. I've seen data sets where you get these mismatched, and you'll have maybe 10,000 polygons in the entire data set. 9,900 are these slivers along the edge. So typically what you need to do is either redraft the data or set a snapping tolerance, or somehow figure out which is the stronger or better or more accurate of the lines that you have, and graph those into both data sets or match the one into the other. You can do some of this automatically, and sometimes it requires a manual pulling of one line to the other so that the data match. So we'll get a lot of practice in the lab in digitizing over the next couple of weeks and building topology. So this is just a real quick introduction.